Excellent and welcome to the TAD Summit online conference. We have a great introductory dive to telecoms from Vance. Now, I think for a lot of people, just treat that as a little recapitulation that we could do with as an industry. But I think for many of especially the TAD Hack crowd, this is a great introduction, and I think Vance provides a very independent view. So rather than it being sort of too telco centric, I think it's got that right balance and can help a lot of people understand some of the really good work that's happened in telecoms over the decades. So, with that said, Vance, over to you. I'm excited to hear what you've got to tell us.
Hey, great. So yeah, I'm going to offer my perspective on things, and it's a very broad topic, and we only have a limited amount of time. So what I wanted to do was to introduce some aspects of telecom, and I'm talking here really about the service provider end of telecom, the infrastructure, the stuff that makes it all happen, that underpins all of how we communicate every day. And that world offers some interesting perspectives. These are very large scale, necessarily reliable networks, and so how do we build things? How do the telcos do it? How do we do it? What's good about that? What's better about the other? That sort of thing.
Yeah.
And so let's dive in. So who am I? I'm the CEO of SigScale. I've been running this company for about 10 years. It's a software development firm, and we make open source software exclusively, and exclusively for the communication service provider market. We build things like our flagship product is an online charging system, so that handles prepaid usage on your cell phone or devices, that sort of thing. So that's where I come from. I've been in telecom my whole life. Since I started as a teenager, I've not worked in any other industries. If I get tired, I'm going to go into filmmaking. But so that's me, and we're going to talk about telecom. Believe it or not, like these are all acronyms that are in this presentation. So telecom has its its own language, and because it's a very old business. We're going to look at the history of that briefly in a moment. Uh, you can't talk about the CSP business without talking about standards. Standards are the underpinning. You don't have single vendor networks, right? We haven't had that. The original wireless networks would come from one vendor. So Motorola provided the handsets, the radios, the all of the pieces in the middle, and everything. But then eventually we started to say, okay, well, we should be able to have other vendors make handsets. Oh, we should have other vendors make radios. We should have other vendors be able to make the switching components that are in the middle, et cetera. And so that when you do that, you need to have specifications for the protocols that allow that to work. And so it's always been very important. The other part of it is that this is a global business, right? So you've got different countries, different governments controlling how things operate in their own country, and so you've got like the ITU-T, the International Telecommunications Union. They set the global standards for things, and have for 100 years. Well, a little less than that, but uh, so. And it's interesting what they do. They don't make specifications; they make recommendations. It's a political thing, but that's the language they use. Anyway, so those are some of the bodies. The 3GPP is the sort of important one that we're going to look at today. That really is the global standards development organization for the mobile industry. Uh, so that we can look at the history of this business because it's really interesting. To really understand how you got someplace, you need to look at the journey that took you there, and it explains some of the reasons why we have what we have. And so again, telecom is it's a vital utility. We have roads and bridges, and we have pipelines. These are all infrastructure facilities that make society run, and telecommunications has for over 100 years been a really important, increasingly important part of that, right? And so historically, it was the government who did that, right? So the government built the roads, and they built the telecom. Uh, and, private industry was always involved in that, but uh, the telephone network itself is mostly around the world was a government agency. We call the PTTs. But as we uh, moved along, we toward the last part of the last century, we had global deregulation. So the timing of what was going on was kind of interesting. So in the 90s, we were transforming the network from analog to digital. So everything originally was analog, and we began to digitize it. Still using copper. Fiber wasn't a thing in the 80s. It was starting to develop, but we used T1s and E1s, and so we were moving from analog to digital, and we were and in the control plane of the network, we were moving to things like SS7. Well, with SS7 and ISDN were digital control protocols. And so now we had these crystal clear, no echo, no delay, no latency, caller's number showing up and caller's name showing up, and features like call forwarding and call diversion and return call. It was the best it had ever been, and this was as we approached the turn of the century, and we were introducing the third generation of wireless networks at the time, with UMTS, which is what we refer to as 3G. And the core technology that was adopted by the service providers and developed by the SDOs was something called asynchronous transfer mode, and that's what everything was based on. So, but as you know, in the 90s, the internet started to happen, and it happened really outside. It wasn't something that was created by the communication service providers. It was an outside influence, and it was something that they were trying to provide. But obviously, they started with the telephone network. Making voice calls was the entire business, and now we've got this burgeoning use case for data, which is taking off, but we need to accommodate both. And ATM was a way to do that. It made compromises, but provided the strict control and quality of service guarantees that the telcos really needed to be able to continue to have the epitome of the technological development that they had just recently achieved. So that's the route they were on. And then suddenly it became obvious that they were going to need to do something else. So in the middle of that 3G development, they pivoted. They just pivoted. The ATM work basically stopped, and they pivoted to IP. And basically a decision was made in the 3GPP and the member organizations that we should stop developing our own protocols, because we have to bear the cost of those, and they're not used outside of this industry, so we're not getting the amortization of the pharmaceutical and the banking industries and everybody else using these same things. So really a decision was made that changing immediately. We're pivoting. We're only going to use IETF protocols, and so suddenly we're going to use voice over IP. We're going to use the SIP protocol for doing voice, and that ATM work was abandoned. Now, this was a major write down and a very painful lesson and painful exercise. Uh, so yeah, because of that, they really just went all in, and so they created. They actually moved to get rid of the circuit switch network at all, so that all of that technological achievement that had culminated in the late 90s, really they began just getting rid of it. And that took a long time, but it did culminated with IMS, which is frankly a bit of a dog's breakfast as a result of those choices. But they made it work, and that's what we have today. And then they started to develop the fourth generation network, and they carried on. So the 4G networks has no circuit switch core, and it uses the IETF diameter protocol for most of the call control, and yeah, so it's IETF protocols systemically in the 4G network. And as you know, we now have 5G, and 5G is rapidly becoming ubiquitous. The 3G network has really been sunset, and we have 4G and we have 5G. And in the 5G core, they're not using diameter. They instead have adopted REST APIs with open API specifications, OAS, as you do today, right? So now the 5G core looks much more like a microservices network that you might be familiar with, but as you'll see, it's not that it's a lot more done in the telco fashion. So let's look at mobile networks. So we have radio access networks, of course, is the distinguishing feature of a mobile network, and so we have radios, and so that is it's seen as a separate network, right? So you build a RAN, and you choose a technology for that RAN, and choose a vendor for it, and or multiple vendors, but and typically the operators do that, right? They won't go single vendor. They'll go 85% Ericsson, and then 10% Nokia, and 5% something else, just to keep everybody honest, and keep it multi-vendor, right? So if you go single vendor and thinking that you're using open standards, you may find out later that it wasn't. Right, so you do try and keep multiple vendors, but most of the phones, or all of the phones really, are using multiple air interface technology. So your iPhone or Android or whatever. Whatever kind of device, IoT device or something, is usually capable of attaching to multiple different air interfaces. There's different bands, the spectrum bands that are used, but also different technologies. So your LTE, 4G radio access technology, and 5G new radio. So you could have a device that does both. And so like we'll see in this picture at the bottom, this is your phone, this user equipment at the bottom. And so that phone is accessing two different technologies of radio access network. And then we have the core network, and so here we've got we're showing the 4G evolved packet core and the 5G core, and this is where all of the control happens, right? So all the authentication and authorization and mobility and the control of everything is in those cores. The RAN networks are really just transport. They're completely under the control. They do nothing on their own, really. They're under the control of the cores. And as I said, that these are packet switch cores. the circuit switch is gone. It's been replaced by IMS. And IMS is a separate network, and it is built on SIP and handles voice over IP, but it is above the packet switch network. So it obviously voice over IP is over IP. So where do you get the IP? The IP is provided by that packet switch core. But IMS provides telephony, the telephony that you're used to dial a phone number and make a phone call, as well as messaging, video calling, and any of the real media involved services are provided by the IMS. The other things that we show here are the PDN. So the packet switched cores are moving the IP around, and you obviously need to get to the internet, for instance, and that is just one example of a external packet data network. And other examples would be like direct to Facebook or direct to Google, and they do that, right? So they'll interconnect directly. So it's not all internet, as well as companies have their own VPN access, which doesn't go over the internet. So large companies will do that. So when you see PDN, you can think internet, but it's really all kinds of data. And PSTN is the old telephone network. So that's how we still communicate globally using the old standards. That's sort of the root of how things work. Increasingly, everything's done over the IP, but you still have that legacy network. It's still out there, so we need to connect to it. It's always part of the architecture. And so again, the distinguishing thing about mobile networks is mobility. We can move around the RAN, moving from cell tower as we drive down the highway, and handoffs occur in the RAN, et cetera. But eventually, you're going to reach the edge of the operator's network. So you need to hand off to another operator. And so we've got we're looking here at a visited public LAN mobile network and a home public LAN mobile network. Those are the terminologies that are used. They're old terms, but so this is the HPLMN is your home operator. That's who you subscribe to. That's where you get your service from. And then if you drive across the border and you start using another operator's network, you can continue to do so because of the agreements between those operators. And the way that works is a bit curious. It's not what you would have expected. So this phone, if you will, this user equipment has attached to the RAN in that visited location, and it of course needs to go through the core in that visited network, but then it is tunneled back to the home network, and the home network remains in control of everything, right? Certainly, they need to control whether you're allowed to use that network, right? And there has to be arrangements for that, and you could have a prepaid service, and all that would be handled by the home network, determining whether you have credit and all of that. And this is more the curious part, that when you access the PSTN, when you're receiving an incoming call, if somebody dials the phone number associated with your phone, that phone number is in the country that you came from, and so that's where it begins, and it will then be rooted in the home PLMN. But the same thing happens when you're making an outbound call. Outbound calls, circuit switch days would be handled by the VPLMN, but with IMS they're not. So you're again routed back. So even though you're in New York, but your HPLMN is in Ireland, that phone call to the Domino's across the street is really going to involve Ireland. And the same is true of the PDN. So when you access your internet, you're accessing it through Ireland. Now there are some optimizations that are done through agreements, but this is the way this is the reference. This is the way it works most of the time. This thing in the middle is called the IPX, and so it doesn't use the internet per se. It uses particular engineered networks. These are IP networks, but they're engineered for this purpose and are provided by a number of different organizations. There's a competitive offer there. So that's the sort of high-level view of those networks. But now we get into the interesting stuff, right? So let's look at architecture. So we've got these different SDOs. We mentioned 3GPP, ETSI, ITU-T are some of the important ones, and they all have adopted the staged approach to standardization, and they use a three-stage approach. And stage one is requirements, and so here at stage one, you're defining something. So pick something like voice call, right? We're going to describe it in a stage one specification. How do you make a voice call on a phone? When we used to have buttons, you'd have a send button, and you'd have the keyboard, the keypad. That man-machine interface would be described. How you use a service. So really nothing to do with technology and all to do with like a human interface, the experience of a user. This is describe the requirements. I mean that call should be clear. It should not have echo. Things. These are the goals that we're going to achieve with the rest of the work. In stage two, we develop a logical model for what we're doing. And so here again, it's technology independent, but we're going to look functionally at the technology that is needed. So what are the requirements on the technology from a functional logical standpoint? So looking at that roaming example, we've got HPLMNs and VPLMNs, the visited network and the home network. So in a logical model, those are roles. That's logically part of the job that we need to do. And having a RAN in the visited network, that plays an important role in this service. And so that's described logically. So what are the functional entities involved? What are the relationships between those entities? So you're defining network functions, you're defining interfaces between network functions, and then further you're defining the information flows. So what information is needed to support the operations across this interface, and those are all defined in stage two specifications. And it's really important that you keep that completely separate from the technology. Because technology evolves quickly, the user requirements kind of never change or glacially slow. But the functional difference, the logical model changes a little more quickly than the user stuff. It does adopt the technology, but it isn't concerned about the protocol of the week. That those can change. So then stage three are those protocols. So at stage three, you're defining wireline protocols. You're defining exactly how you encode the information described in stage two on the interface described in stage two to exchange it with another network element. So the actual how you pack the bits on the wire and send it across the interface from network function one to network function two, is a stage 3 specification. And you can have many stage 3 specifications for the same stage 2. So stage 2 is defining that you've got network function A and B, and you've got an interaction between those, and we can have 3 or 4 different protocols, or however many, that are alternatives for accomplishing that. And even if you developed a proprietary way of doing that, that could be acceptable, but you would have to move the same information and perform the same function to fit in the overall network, right? So keeping the stage 2 and stage 3 separate is really important, and this is a failure of most less organized standards development work. And so at stage 2, we've got again, we're looking logically, talking about network functions and interfaces, but we're also talking about the information. So we're modeling the information. You hear data model used all the time, but a data model is secondary to information model. So at stage 2, we've defined what kind of information do you need to exchange between these two network functions. I need the telephone number. I need the IMSI, which is the identity on the SIM. This is so those are two types of information, and they need to be exchanged. It doesn't matter how they get exchanged, but that information is always going to be there, no matter what the technology choices are. So you again keep that separate, and this diagram here comes from other work that I've done, looking at the management plane, and this is a real life example from the 3GPP standards, where we look at the management of a 5G core AMF function, access and mobility function, plays a key role in the 5G core. You have one information model at stage 2, and there are 3 different choices for stage 3 to represent managing that AMF. And so we've got Yang, which is a data modeling language by the IETF. You've got JSON schema, which people are quite familiar with these days. But again, it's not. JSON is what would be on the wire. JSON schema is how you model it. So these are all different data models, right? And XML schema again. So you might use XML on the wire. Your data model would be an XML schema. The important thing about this is, because they are all based on the same stage 2 information model, that these are interchangeable. And so when we move from one protocol to another, when we upgrade from an older XML version to a Yang version or to a JSON version, we're going to be encoding the same information. And so that one interface between two functions has had its protocol change, has no effect on the end-to-end use across the network, right? You've achieved the same thing, you've just coded it differently. And next year, when we decide we're going to use gRPC, we're gonna base a data model for that on the information model and accomplish that without too much trouble. So this is the strictly organized way that standards and development takes place in the telecom world, and it is a pretty good lesson for the rest of us. Lastly, with the architecture stuff, it's important to get this perspective that there are different perspectives. So if we look at a network, and here we've got this gray cloud in the background, so that represents a network, we've got these different slices offering perspectives across that network. So when we're looking at these specifications, we're always looking within one of these planes. So like if you have architectural diagrams for a building, you'll have like the typical floor plan, which is like looking from the top down. That's a top-down perspective. But when you want to understand how the walls work, you have a perspective from the side, right? So when we're looking at things, we're always really scoped to one of these planes. The user plane is the bare traffic. So if I'm using the network for this video call, uh, that the video and the voice and the data associated with it is all flowing across the user plane. That's the data plane, the user plane. So routers and gateways and things like that. The control plane is where we exchange information between network functions in order to make that happen. So the authentication and the authorization and the routing, like going to the simple telephone call analogy, when I key in my digits, the digits cross the control plane. So they're sent to somewhere where they're analyzed, where a routing decision is made, and then it needs to control the user plane to set up a connection to get me to the next place, et cetera. So the control plane is where all that happens. And it's more important in telecom than a lot of other things because these actually use different network functions and different network interfaces and follow a completely different path. So you've got different network functions involved in the control than you do in the user plane. And so when we're looking at it, we've got a different topology with a different set of network functions for the control plane. The management plane is what's used for provisioning, for observability, for billing, charging, all of that sort of thing. So again, those are perspectives. All right. So if we look at network architecture, so we introduced the 4G Evolved Packet Core, the 5G core, the IMS, IP multimedia system, where we do telephony and video and stuff. So if we look at the 4G network, 4G is still predominantly what's used in the mobile networks today. Even when you're using 5G, you're using a 5G radio access network, and and from there you're going to the 4G core. That's what we call 5G non-standalone. 5G standalone is where you would use the 5G core, but there's less of that implemented today. Although that's clearly what everything's moving to. But here we're looking at 4G then. And so these are some of the network, these are most of the important network functions. There's a lot more, right, for a lot of different things, but these are the key ones. So your UE obviously has an air interface to the radio access network. That's this UU interface. So these lines are that stage 2 specification. So these are logical entities. These don't translate necessarily directly to physical pieces of equipment or to products that you would buy from a vendor. They, for instance, the SGW and the PGW are always implemented in one product. So you've got the Acme Evolved Packet Core Gateway, and it performs a number of functions, and those functions would usually include the PGW, and the SGW might include the MME. So that relationship is separate. So this is logical. So this is a stage 2 representation. And in those stage 2 specs, we're naming what these network functions are, and we're naming these interfaces. So in the logical model, there's an important interaction between a serving gateway and a PDN gateway, and that interface is given the label S5, so we can talk about the S5 interface, and we can create multiple protocol specifications at stage 3 that describe the S5 interface. Um, and so yeah, these are the basic things here. So MME is handling the mobility. So this UE is physically going to use this air interface UU over the RAN, and the RAN is connected into the core. So these top two levels here are part of the evolved packet core, and the RAN, the PDN, of course, is external. The UE and the RAN are outside of the core. So the connection from the RAN to the core is accomplished here, and the MME using this control plane interface will uh, uh, get the communication. So the communication between the UE and the MME, this is not a physical interface at all. This is a logical interface that this communication is taking place over UU, S1U, and S11, but the logical interconnection is directly here. After we've accomplished that, we're moving information and performing operations across there. We call that the S1 MME interface. The HSS is the home subscriber server that contains all the subscriber data, and it's consolidated there along with the authentication key secrets that are necessary, that are shared only between the HSS and the SIM and the UE. So this is an important interface for that. And we've got the PCRF, which does policy control. So here with the PCRF and the online charging system, these elements are bridging to the commercial area of the business. So deciding what policies you're allowed. What did you subscribe to? You may be allowed a faster service than someone else because you subscribe to something different. And the OCS is used for prepaid. So it's keeping track of whether you've got enough balance to do that. And as you use services in real time, it rates them. And so this SY, GX, and GY interface, these are using diameter. So that's the evolved packet core, gives you a feel for how that gets put together. Again, 5G core is what we're moving to, a lot less of this deployed today. And this is very similar. And instead of the HSS, we have the UDM, and the actual SIM secrets and that sort of thing are handled by the authentication service function. And the PCF is the 5G version of the PCRF that handles policy control. And the CHF is the charging function, and that's handling that online charging function, the same basic things. So the AMF, that combines the MME and the serving gateway functions. Well, sorry, it's really more the MME. The SMF is a control plane function for handling the use of the control of the bearer networks, and the UPF, which we've shown at the bottom here, is part of the data plane. So the data path is from the UE through the RAN into the UPF and out to the PDN, the internet. And so these are control plane functions at the top, and these would be the UPF is a user plane function. And then we can look at IMS. Again, that's that VoIP SIP-based network. And this thing is a bit curious. You know, the IMS was, I told you about the curious timing and the politics kind of behind that. But if you think about what is SIP, SIP was developed to be a peer-to-peer protocol. It was developed to go completely over the internet, directly with no control from any kind of telco or anything. That was the whole point. But they decided to adopt it for the sort of political and business driver reasons that I mentioned earlier. So now they've got a peer-to-peer protocol, but they necessarily need to do centralized control to be able to charge for it and manage it, et cetera. So they've co-opted this peer-to-peer protocol and turned it into a centralized control system. And so that centralized control takes place in this call session control function. So we've got a number of different ones: the proxy call session control function, the aggregating call session control function, and the main one in the middle is the serving call session control function. This is the same HSS from the EPC. So that's where your subscriber information is. This is the same OCS from the EPC for charging. Application servers are where all the real the application level stuff takes place. So if you're using telephony features like call forwarding and stuff, it's all done through an application server. But these call session control functions are SIP proxies. So you're using SIP and it's being routed through these proxies. And it's kind of curious how that happens. We'll look at that next. Well, in the next section. Yeah, we're running out of time, so I'm gonna. We get into the meaty stuff here. So one of the things I'd like to throw in here is the IETF SIGTRAN working group developed a new protocol for telecom, right? So you may have heard of SCTP. So SCTP is at the same level as UDP and TCP. So it's an IP protocol, but it doesn't go over UDP or over TCP. It's a peer to that, right? And it's the stream control transport protocol, and it accomplishes some things that were important to be able to do the telephony signaling. We're moving that SS7 signaling and very stringent quality of service. It solves some problems that aren't solved by UDP and TCP. It supports use cases for both TCP and UDP. But one of the things that it does that makes it unique is it does multi-homing. So, as a developer, you'll be familiar with the concept of a socket. You open a TCP socket or a UDP socket and communicate across that. Here, you open an SCTP socket, but that socket can be associated with different IP addresses on different interfaces and therefore different networks. And so the path between the two endpoints is multi-homed. So if you lose one entire network or one entire Ethernet interface on your host, you still communicate without any loss. And the other thing it does is over TCP. TCP is one connection, so it suffers from head-of-line blocking. So if you've got multiple sources putting information onto the pipe, reading out at the if one of them puts too much on, like bearer traffic, and you're trying to get control traffic through, that control traffic may have to wait until the bearer traffic gets through. But with SCTP, you've got multiple streams. And so you're only going to be suffering head-of-line blocking on one stream. And if you put it on another stream, well, that one's unimpeded. So that's that, which is an interesting perspective and quite different for telecom. That's not used outside of telecom very much at all. We looked at I mentioned the diameter protocol. So with diameter, it runs over either TCP or SCTP. We use both a lot. And here it's a client server thing. So you've got relays that can have connections, but you've got the idea of a session between a client and a server. And so this becomes a bit of a network that it is a network, but it relays things at the diameter level. So if we, and this is a kind of an important point I wanted to make about this is the way we do things. So we don't do load balancers. You're not going to find a load balancer anywhere in this architecture. there's nothing labeled load balancer. Like nothing really has that function. And why is that? Well, because when you design an end-to-end network, designing a load balancer would really be a failure. You're now, don't get your backup about that. You're never doing that. 3GPP, they're building the entire network. Even they control the phone, so they can do it end to end. But normally doing it end to end, you have no control over that user on their browser or whatever. So you introduce load balancers at the edge, but we have in an end-to-end network, we don't do that. So if we look at diameter, for instance, what happens is you'll have a one network function, which is the client in this client-server arrangement, and so we will refer to that as the origin host. So in respect to the session going from client to server, we've got an origin and a destination, and so then this network function will maintain these peer connections to multiple destinations. And so if that network function knows about 3 diameter peers that are either the actual network function needs to talk to. So quite often that's the way it works. Like the SGW may have a direct peer connection to the OCS to exchange that charging information. Or we may introduce diameter routers to handle the relay. But in either case, the normal way to do it is that this client's going to maintain multiple sessions as alternatives in round robin or some sort of distribution across those. So that's just the normal way it's done. Although the last point about that is that diameter does have session affinity. So you may choose a specific destination host, but once chosen for that session, everything continues across that particular. Although if it's in a relay, that connection is limited to the first hop. Well, sorry, that's not true. It's the end relationship is what I'm saying, but it's not limited to the first hop. So it doesn't matter how what path through the relays you take, but the point is that the session is from one origin host to one destination host. But you'll do that routing based on destination realm at first to find to select that destination host. And so then this is what it looks like when you introduce those relay agents. So we call those diameter routing agents, and those are products that you buy like in a similar way that you'd buy an SGW or a router. And again, in this sort of a network, you're still going to have your clients be multipath. So you're always connected to more than one way to send that, but then it can fan out and be quite large after that. So it can't really handle any level of scale. And quickly, in the IMS, we use SIP, and I did mention that everything goes through this call session control function. And so this is the message sequence for that. And it's curious how it does this, right? So the UE always goes through the proxy. It uses an interrogating call session control function, which is going to interact with that home subscriber server to get the subscriber information like authentication. But this interrogating server is going to be involved in choosing an SCSCF. So again, you've got the opportunity to scale that out. So you're always getting to the proxy is one thing. So the proxy selecting and interrogating CSCF is the next opportunity to fan out. And then at the interrogating, it can fan out globally, really. And so you can scale infinitely with that. Although it is, this is what I meant when I said it's a bit kludgy. Well, I didn't use the word kludge, but I guess I just did now. If you look at so how application servers end up routed, I said they're all routed through this the serving CSCF, and that ends up looking a little weird, right? So the SIP message goes through the proxy and the interrogating and ends up at the SCCF, and then it has these initial filtering criteria which establish a pattern matching against things to decide how to route how the SIP proxy does its routing of SIP messages. And the way you introduce application servers is through matching with these IFCs, which are actually stored in the HSS and downloaded as part of the subscriber information to the CSCF. And so then it will understand that this subscriber needs to use the multimedia telephony application server. That's where your phone calls and supplementary features are going to be done. But there may be some value-added server, like maybe your enterprise service requires that all the calls be recorded. So it's going to involve that specific value-added server. And so these are actually SIP, like a SIP invite comes in, a SIP invite goes out, a SIP invite comes back, SIP invite goes out, it comes back, it goes out to the next hop. It's again, it looks pretty strange, but that's how it's done. And then finally, we look at 5G. So in 5G, we have what we call service-based interfaces. They're REST, right? They're open API specifications, OAS, Swagger, that sort of thing. And so, this looks a lot more familiar to you, right? But again, it is and it isn't, right? So you're going to find, because it's telecom, it's very structured, right? And a lot of consideration goes into these specifications for resilience and scalability and everything else. And so this really shows an example. The NRF is it's a network function repository function, and you can use this for discovery. So this network function may have just come to life. It's just been instantiated inside the Kubernetes or whatever, and now this instance needs it's an AMF and it needs to talk to an SMF. So where are the SMFs? So it can do a REST query against the network repository function, and here in this example, it's saying, well, I'm a requester. Oh, I didn't put the type in there. That was a typo. But this is the kind of network function I am, and the kind of network function I'm looking for is a CHF. So this was the example of looking for a charging function. And so we get back, well, there's a number of NF instances. And then for this particular instance, there's its identity, there's its type, there's its status. So we can find out the fully qualified domain name, and we can get a list of IP addresses. You can have either or both of those things. So here's one instance of a CHF with multiple endpoints. So again, you've got that fan out going on for reliability and resilience and scalability. And then this is an array, actually, so there may be multiple instances. So that is that's a host. These IP addresses could represent different pods in a Kubernetes stateful set or something like that, whereas another instance would be another one that's maybe geographically different or whatever. But that's how that kind of fans out. And then the very last thing here is I've shown an example of how we can take those principles and apply them to what we are used to doing, right? So if you think, yeah, maybe there's something to this no load balancer thing, maybe moving that fan out closer to the consumer is the way to go. So here's an example of something we do at SigScale. And so we've got a network function, and that network function will interact with its configuration. So it finds out what the base URI for a service it needs is. And so here's that in this example. Um, and and then so this is given as a URI with a domain name for a host. And what he can do is use the host resolver to do a domain name service type resolution. Now, it could be using the Etsy host file or whatever, but you've always got a resolver on the host. So use the local resolver to look this up, and then get back a list of IP addresses that are assigned that are available for that host. And then he can go to configuration, look up what the sort algorithm is, and look up HTTP options he should use. And so here he's finding, let's just randomly choose one of these addresses to try and communicate with, and let's configure a timeout of 1.5 seconds. And so he'll send the post. And it turns out that something, either this host is down or the network, it's unreachable. So normally that TCP connect will just sit there for like 70 seconds, a minute and a half or more, and then eventually time out. Well, that's too long. Like, everybody's given up at that point in time. So what we can do is set a more reasonable timeout. So this configuration says, okay, only wait a second and a half. And so after a second and a half, this will fail, and so then he'll go on and choose another randomly choose another one of these addresses, and then establish that connection and find out that he can reach network function 1. And so there we've accomplished the same sort of architectural method that's used with diameter and some of the other principles in the telecom world. And that's the end.
Wow. Well done, Vance. That was impressive. Congratulations. For me, I have never seen a more complete view of the telco stack. So I think that was impressive. It's a single resource. You can review this and it gives you everything you need. And I do love the term you used for an IMS at the beginning, which was dog's breakfast. And
Yeah.
you clearly showed why it's that, because it was, there was the SIP view of the world, and then, but we need control. And I remember all the sniping at each other from the SIP crowd and then the IMS crowd. But it's there, it's deployed. And 5G and 5G standalone is rolling out, albeit slowly. But
And
cool.
IMS is still how you accomplish that in 5G.
Correct. Correct. Absolutely. 100%. Now, I know, Slava, you provided a list of questions for Vance. What I'd suggest is, Vance, if you could go through those questions and we could write up some answers to them so we can get this content as an atomic piece so that I can send it to the TADAC community, because they're predominantly web developers. So for them, where you're getting to, I think it's very interesting given what they do day to day. So this sort of brings it all full circle to what they understand, which is from a web architecture perspective. So that's why I'm so keen that we finish on HTTP. But what I suggest for the sake of time, well done, Vance. Let's get this all wrapped up, a big bow on top, and make it a resource that people come back to time and time again. Because the thing I'd advise is, yes, it's complex. Yes, at first glance, it does seem, a little daunting, but give it time. Bite off little chunks, and in time, you'll get your head around what this is doing. Slava,
Right.
do you want to?
Yeah, well, basically, I'm not sure that. Yeah, the telecom stack is itself is complex, but it pretty easy learn if you have the some mentors like Vance, for example.
Yes.
Because I when I was first jumping to the some telecom project, we had some seniors of the developers who was deeply who deeply know the
Yeah.
LLM HTTP itself and the telecom stack, and even I ask any questions, I had the one clear answer like go ahead to read some 3GPP mobile specification. Go ahead to read some documentation without any. So if I was back to the that time, and this was the hell for me actually. And if I will be back to this time, and I was get this some presentation like once shown today,
Yes.
it's speed up my my way to the learning and get knowledge for in the telecom side. It's
Yes.
pretty fast, yeah.
Oh
So
yeah. And its completeness. It's just he covered it all. That's why I was so impressed in what he achieved. But again, Jared,
Broadly and quickly.
oh yeah, exactly. That's what people need. It's because it's all so deep dive, deep dive, deep dive, and you get lost in all the details. And that's why I loved what you did. So again, Jared, Matthew, thanks so much for joining us as well. And I'll get this all written up and bring the Vance's answers to Slava's questions in that summary as well. So well done, everybody. This is a great piece of work.